At the end of this lecture, participants should be able to describe graph, their types, and composition of a graph. To apply graph in solving traversal problems and other applications, to determine whether a connected graph has Euler circuit of path or Hamilton circuit of path, and finally, to be able to represent graph as adjacency matrix or incidence matrix. First of all, what is a graph? G. A graph, which can be represented by the letter G, is composed of vertices and edges. A graph is a nonlinear data structure that consists of nodes and edge pairs of objects connected by links. A graph is made up of vertices, a set of vertices, and a set of edges. Let's look at this example of a graph. This graph has multiple vertices which are labeled by letters. The letters of the vertices are S, W, Y, Z, U, X, and V. E here refers to the edge, whereas all the nodes or points are vertices, each one with a label. Now, this can be represented as a set, as you can see here. S, U, V, W, X, Y, Z represents the nodes, but having just vertices is not enough because the vertices can be connected differently. Therefore, we also need the set of edges. The set of edges is made up of a pair of vertices. A pair of vertices such as XS indicate that there is an edge connecting X to S. So this edge, this line is what we call edge. And as you can see here, all the lines, all the edges here are represented by the pairs within the E set. Graph traversal. It is a technique used to search for a vertex in a graph. It is also used to decide the order of vertices to be visited in a search process. Now, to understand this, let's look at a problem. The problem that we would like to highlight here is the Königsberg bridges, which is mentioned by a mathematician by the name of Leonhard Euler in 1736. He wrote a solution to a problem concerning the geometry of a place. It is the first paper in graph theory. So what is this problem of Königsberg bridges about? Now, assume that this image is showing a river and there's an island in the center. The island is called D, and then the adjacent banks are A, B, C. These are the land masses. All right. Now, there are a few bridges connecting these land masses. All right. There are 1, 2, 3, 4, 5, 6, 7 bridges. So the problem of the Königsberg bridges state that starting and ending at the same point, is it possible to cross all 7 bridges just once and return to the starting point? Let's take A as the starting point. Is it possible for us to cross all the bridges only one time and finally to get back to the starting point? Now let's try one instance. Let's say I take this bridge. Look at my cursor. From A, I take this bridge. All right. And then I take this bridge. And take this bridge to B. I take this bridge to C. I take this bridge to D. I take this bridge to C. Oh, I won't be able to get back to point A. Okay, let's try to take this bridge to get back to point A. D and A. But wait, the problem is that we have been crossing same bridges more than one time. So this has violated the statement of the problem. So our solution, our attention does not solve the Königsberg bridges. So in the first place, we need to address the possibility that this can be done. Is it possible or not? There may be a possibility that this cannot be done. You have to cross the bridge. You have to cross the bridge, the same bridge, more than one time in order to achieve the feat of starting from the same point and ending at the same point. Now, this can be done for B, C, D, doesn't matter, yeah? The problem requires us to come back to the starting point after crossing every single bridge, but only one time. So let's hold up the answer for this. Let's hold up the solution for this. We shall look at some of the theories behind graph traversal. And finally, we're going to address this problem in somewhere in the middle of the lesson. So edges. An edge may be labeled by a pair of vertices. For instance, E represented by a pair of vertices V and W. See here, the round bracket indicates that there are a pair, and the line connecting these two vertices is the edge that we are talking about. E is said, the edge is said to be incident on V and W. The word incident means that it is an edge connecting the two vertices, incident. Isolated vertex is a vertex without incident edges. Now, in this example, we have three vertices, right? Three vertices, three vertex, okay? Vertex V, vertex W, and there's one isolated vertex. Why is it called isolated? Because there's not a single line connecting this isolated vertex to any other vertex, a vertex without incident edges. There are some special edges on top of the simpler ones that we have seen earlier. Parallel edges. Look at the lines between A and B, the edges between A and B. There are two lines connecting A and B, all right? One is a curve, one is a straight line. Now, these are considered parallel edges because these two lines, these two edges are connecting the same vertices. Now, the other one is a loop. Now, look at vertex D. So there is a line that does not connect D to any other vertex, but is reconnecting back to itself. This is what we call D having a loop, whereas A and B have two parallel edges. A graph is said to be a simple graph if, when we check the graph, we don't find any loops nor any parallel edges. Like in this example, can you find any parallel edges or any single loop? Not even one, right? So it is a simple graph. Whereas the previous example, this is not a simple graph because we have loop and parallel edges. Now let's look at the second graph on slide 7. Note that a part of the vertices V1, V2, V3, V4, and V5, and the edges connecting V5, V1, V1 to V2, V2 to V3, V2 to V4, V2 to V5, and V4 to V1, and V4 to V5. A part of the vertices and edges, we have numbers assigned to the edges. Look at the numbers. These numbers indicate the strength of the edge. Yeah, we call this weights. Now, this weight is just a generic representation of the strength of the edge. We can see in multiple ways depending on how depending on the application. For example, if we are talking about geographical places, like for example, between towns, and the lines represent the distance between the towns. So the numbers here, the weights here could probably be distance. Yeah. But if you are talking about other application, for example, the vertices are representing servers, and the distance between the vertices are given by the number of loops the packets have to go through. Then the numbers here will not represent a distance in kilometers, but the number of loops. So what I would like to highlight here is that the weight is a magnitude of the strength of the edges, and depending on the application, they may mean differently. Now, what is different in this graph? In this graph, we see arrows. Yeah, we see arrows. This indicates that there is a particular direction. We cannot say B to A, but we can say that the edge is connecting A to B, but not B to A, because there's only one arrow, yeah, which is A to B. Is it possible for us to represent B to A? Yes, we just need to change the direction of the arrow. But what if there are two directions, A to B and B to A? In that case, we need to have another edge, another parallel edge with the arrow pointing from B to A, yeah, a part of the existing edge pointing A to B. The key point here is that a graph that has direction, yeah, indicated by the arrows on the edges, are called directed graphs, or for short form, digraphs. Now, what is the use of graphs? Why do we bother learning about graphs? Graph is for modeling data. There are many problems in real life that can be represented by a graph. So if you can represent the problem as a graph, then we may be able to solve the problems as a graph problem. And this is useful because in the next few slides, we are going to learn about problem solving using graph. And problem solving using graph can be used in the future for different kinds of problems. Some of the problems that can be solved using graph theories are network packet traffic, internet protocol, telephone network calls, especially long distance calls. We have different connectivity between different telephone networks, right? Between countries. How do we link these networks up economically? Yeah. And then neural networks, which is about in the field of medical science, will be about how different neural cells or brain cells are connected to one another. In artificial intelligence, we also have emulation of biological neural networks in the form of computing nodes. Then we also have social network. Social network is an example of using a graph. Social networks such as Facebook and much older Friendster, and of course contemporary to Facebook will be Twitter and many more. The friendship, the multi-tiers of friendship or affiliations of individuals is forming the social network, and we can analyze how close one person into another, the interest of one person by associating this particular individual with the group that this person is associated with. And graph is also used for the study of infectious disease. Like for example, now COVID-19 is highly infectious, and people who are in contact with a person diagnosed with COVID may become a potential carrier or patient, and we need to study how this disease spread, and therefore strategies for containing this disease. This is where graph problem can be applied in. How different proteins interact in a DNA chain, yeah, in biological science. How we connect different flights. For example, you want to take a flight from Malaysia to Newark Airport in New York. Probably there's no direct flight. There'll be transition flights in between. So how do we connect these flights in the most economical way? Yeah. And then train connectivity, we want to get from one place to another place. We may not be able to find a direct train going from one point to another point, but we may be able to combine a few different train routes in order to get to the destination that we desire. So this is where graphs can be useful. Now let's look at one simple exercise about flight networks, and let's see how a daily problem, yeah, at work or in the industry or in life can be turned into a graph problem. Every day there are 4 flights from Boston to Newark, 2 flights from Newark to Boston, 3 flights from Newark to Miami, 2 flights from Miami to Newark, 1 flight from Newark to Detroit, 2 flights from Detroit to Newark, 3 flights from Newark to Washington, 2 flights from Washington to Newark, and 1 flight from Washington to Miami. Wow, isn't this confusing? How nice if we are able to represent this in a kind of drawing, yeah, in a kind of abstraction. This is where graph comes in. So we need to draw a graph model of the airline routes between these cities. These cities are Boston, New York, Miami, Detroit, Washington. Yeah, I think about 5, 6 of them. Now, there are 5 graph models that we are going to draw because there are a few criteria. Yeah. Number 1, a graph model of the airline routes between the cities where an edge between vertices represents cities that have a flight between them in either direction. Notice the color. Yeah, these are the important keywords that we need to understand later on how to draw the graph. B, an edge between vertices representing cities for each flight that operates between them. See, each flight that operates between them is the keyword. An edge between vertices representing cities for each flight operating between them in either direction. Either direction is another important keyword here actually. Plus a loop for a special trip that takes off and lands in Miami. So there's a loop in the city of Miami. So does this ring a bell to you about loop in a graph? And then D, an edge from a vertex representing a city where a flight starts to the vertex representing the city where it ends. So flight starting from one point, ending another point. Sounds like a digraph, right? Directional graph. And then E, an edge for each flight from a vertex representing a city where the flight begins to the vertex representing the city where the flight ends. So each flight and from beginning to the end. Now, not to worry. At this point of time, probably you feel all these requirements sound similar. We are going to look at them one by one and produce the corresponding graph model. Then you'll be able to understand, yeah? So let's look at the first one. Answer for the first one. An edge between vertices represents cities that have a flight between them in either direction. So we have 5 cities just now: Detroit, Boston, New York, Miami, Washington. By reading these sentences, right, I think you can extract how these cities are connected. So do it step by step carefully, then we'll be able to produce a graph that looks like this. Apparently there's no direct flight from Washington to Detroit. If you wish to get to Detroit from Washington, what you can do is probably you take a flight to Newark, and from Newark to Detroit. Is there a direct flight to Miami? Yes, there's a direct flight to Miami. You don't have to go to Newark in order to go to Miami. So you see, this is how it may be useful. Now, how do we produce this graph? It says in either direction. That means Washington to Miami, Miami to Washington, Washington to New York, New York to Washington. There's no direction. Yeah, in both directions. It means in both directions. So in this case, we don't need to draw the arrows because it is in both directions. Now let's look at the answer for the second requirement, B. and edge between vertices representing cities for each flight that operates between them. Okay, that operates between them. Now, you see here, every day there are 4 flights from Boston to Newark. 4 flights from Boston to Newark. Boston, where's Boston? This is Boston. And where's Newark? Okay, Newark is here. 1, 2, 3, 4. Okay, there are 4 flights, and then another 2 here probably. Is moving in the other direction. Let's find out. Newark, Boston. Okay, every day there are 4 flights from Boston to Newark. 2 flights from Newark to Boston, you see? 4 flights Boston to Newark. 4 flights B to N. 2 flights N to B. All right. So possibly we can draw arrows here to show the directions. Yeah. But because it doesn't specifically mention the need for that, so I think it's all right to leave it like this. You may be wondering why, instead of drawing each flight route, yeah, why don't we just use exactly similar ones like the answer in A, and we put weights. Yeah, we put weights from Boston to Newark. We draw the arrow, Boston to Newark, and then we draw another parallel edge from Newark to Boston, and we put a weight 2. Is that possible? The answer is yes, you can do that too. That's also equally correct. Now let's look at the question for C. An edge between vertices representing cities for each flight operates between them in either direction. Because in either direction, it mentions in either direction means we don't need to put the arrow because it's in both ways, yeah. Plus, and look for a special trip that takes off and lands in Miami. So basically, the answer for C and B are actually similar. What is different? The difference is that there's an additional information plus a loop for a special trip that takes off and lands in Miami. So this is where the loop is. All right. And then what is indeed an edge from a vertex representing a city where a flight starts to the vertex representing the city where it ends. Okay, so there is a starting point, ending point. Therefore, there is a need. It's not bidirectional. There's a need to point out the arrows, the direction. That's when you have to add the arrows. Yeah. Now, why do I have a different routes? Let's say from Newark to Boston. You see here I have 4 routes, right, from Newark to Boston. Why do I do that? Well, because here it doesn't say for each. It doesn't say for each flight. Yeah, it just say an edge that represents all the routes. That's why it's okay to have only one line to represent the 4 routes. Yeah. You can argue with me about this. Probably you may say that, okay, why don't we put the weight 4 here, weight 2 from Boston to Newark? I will say that you're right. Please go ahead. No problem with that. And finally, for E, an edge for each flight. You see, each flight from a vertex representing a city where the flight begins to the vertex representing the city where the flight ends. So each flight ends. So each flight you need to draw the individual flights begin and ends, indicate there's a need for an arrow. All right. Okay, let's move on. The terminology path. Path is the route taken within the graph, and a path may have length. A path of length 7, okay, in this example, yeah, we have how many vertices here? 1, 2, 3, 4, 5, 6, 7. That's why it's called path of length 7. Yeah. So how many vertices actually you have? So the starting point, there's one vertex. You remember vertex is actually a point. Yeah. 1 point, 2 point, 3 point, 4 point, 5 point, 6 point, 7 point, 8 points. 8 points. How many edges? 1, 2, 3, 4, 5, 6, 7. So for 7 edges, we need 8 points. Yeah, we need 8 vertices. And if we know that there are 8 vertices all connected linearly, there's definitely 8 minus 1 edges. All right. Now let's look at the second example. It is of length 9. Let's say we start from this point. we want to count the length, right? Which means we count the edges. We are not counting the vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 edges. Therefore, length 9. Why is it not called path? Why is it called cycle? Now, cycle is a path where the end leads back to the starting point. That's why it's called a cycle, because if you follow the path, eventually get back to the starting point. A cycle is a path that begins and ends at the same vertex. Now, remember Euler and the Königsberg bridge? So let's revisit that problem, yeah, by learning about Euler cycle. So Euler cycle is a graph. It's a cycle graph, not a path, because it's not just a path, but it's a cycle because the starting and ending point is the same, which is exactly the problem of Königsberg bridge, whereby we want to start and end at the same point. And Euler cycle requires that passing the edges only once. I repeat, the main feature of Euler cycle is that starting point, ending point is same, and all the edges you pass only once. That's the main criteria of Euler cycle, which is the problem of the Königsberg bridge. Now let's look at this Königsberg bridge image and how we can represent this as a graph problem. Because if we can represent it as a graph, then we can treat it as a graph problem and solve it as a graph, right? So this is how we can apply graph. So let's look at the graph here, whether it is correctly representing the actual Königsberg bridges. How you draw it does not matter, but there are a few criteria that must be fulfilled. Number one, you need to represent all the vertices. Okay, we have A, B, C, D, A, B, C, D, and more importantly, how are these vertices connected? Okay, let's look at between A and D. Yeah, A and D, there are two bridges, right? So you see, between A and D, there are two bridges, two parallel edges. All right. And then let's do this systematically. A with D. Okay, how about with others? Is there any? Yes, with B. With B. So A goes to B, only one line. Okay, so we're done with A. Forget about A now. Let's go to B. B is connected to A. Okay, fine. The previous line. B is also connected to D, so we need to draw one line to D. B is connected to C. This is new. So B connects to C. Any more? No more? Okay, let's move to C. C connects to D. There are two lines connecting to D and one line connecting to B. As we know, just now B to C, C to B, so it's the same line. C to D, two lines. So again, you see, there are two parallel edges or two parallel lines between C and D. Now, finally, D. Okay, let's double check. D is connected two lines to A. Okay, fine. D is connected one line to B. Fine. D is connected two lines to C. Okay, two parallel lines, two parallel edges to C. Fine. So this graph is accurately representing the Königsberg bridges. Now, how you want to draw it, the orientation, whether you want to put A at the bottom or at the top or to the left, to the right, doesn't matter. Yeah, the length doesn't matter, but the connections must be correct. Now, before we solve the Königsberg bridges problem, let us study one concept that is very important to solve the Euler problem. Let's get to know degree of a vertex. What is meant by degree of a vertex? The degree of a vertex is referring to the number. So this is where you need to count the number of incident edges. Remember what incident is from earlier slide? Incident means edges that are connected to that particular vertex. Now let's look at A. Okay, vertex A. So we have number of vertices here. Yeah? A, B, C, D, E, F, G. Yeah, one vertex, many vertices. So vertices is the plural of vertex. Is the plural of vertice. Yeah, the plural of vertex or the plural of vertice is vertices. So we have a vertice of vertex A, B, C, D, E, F, G. All right, and now we want to figure out the degree of vertex. So we are going to use the symbol delta and then the particular vertex. Yeah, vertices. So let's start with A. The degree of A. Let's count how many edges. 1, 2, 3, 4. So there are 4 edges connected to A. So we put 4 for A. How about B? 1, 2, 3. So there you go, 3. How about C? 1, 2, 3. Wait, 1, 2, 3, 4. So C has 4 edges, incident edges. So it's called, that's why the degree for C is 4. And so on and so forth. We can work them out and they're equally correct. Let's just test the last one. G. 1, 2, 3. 3 incident vertices. So you see, the degree of G is 3. So now you know how to count the degree of every vertices, right? So you need to know that. Now, how do we apply this to the Euler graph? If you're able to apply this to the Euler graph, we may be able to solve the Königsberg bridges problem. So this is a theorem that we need to remember. If the graph is a Euler graph, that means not all graphs are Euler. If it is a Euler graph, yeah, if and only if the G is connected, that means all the vertices are somewhat connected, yeah, and all the vertices have even degree, all the vertices have even degree. What does that mean? What is meant by even? The opposite of even is odd, right? So even means numbers like 2, 4, 6, 8, 10, yeah, multiplication of 2. Odd is 1, 3, 5, 7, 9, non-multiplication of 2. Yeah, so that is the mathematics, arithmetics. Yeah, and let's see how we can apply this. So in order to solve this Königsberg bridges problem, first we represent this as a graph, and then we need to figure out the degree of each vertex. Yeah, A, how many? 1, 2, 3. B, 3. C, 3. D, 1, 2, 3, 4, 5. So you see here, degree A, B, C, D, 3, 3, 3, 5. What is the nature of the numbers of each vertices? Are they even or odd? They're even, right? No, they're not even. They are odd, right? Like I said just now, even numbers are 2, 4, 6, 8. They are multiplies of 2. Whereas odds are non-even. So 3, 5, 3, 3, 3, 5. All these are odd numbers. So you see, it is not a Euler graph because Euler graph must be even. All of them must be even. If one of them is odd, sorry, it is not a Euler graph. In this case, A, B, C, D is not a Euler graph. And if it is not a Euler graph, it means that there's no way where we can start from the same point and end at the same point and only going through all the edges one time only. So now we know that Königsberg bridge cannot be solved. The Königsberg bridges cannot be solved because there's no way we can get from point A and back to point A crossing every bridge only one time. Yeah, we have to cross the same bridge more than one time. Some of the bridges. All right. So you see, this is an application of Euler graph. In this classic example, where Euler graph is first introduced, the application is on Königsberg bridges. Okay, another interesting theorem on the degrees of the graph is that if you total up all the degrees, yeah, if you total all the degrees, it's always an even number. It's always an even number. You see, if you have n vertices, okay, and m edges, n vertices and m edges, when we total up the degree of every vertices of that particular graph, we will get an even number, which is a multiplication of 2. Don't believe me? Let's take a look at the Königsberg bridges again. So we know that the number of vertex here is A, B, C, D. So there are 4 vertices. And how many edges? 1, 2, 3, 4, 5, 6, 7. 7 edges. Number of edges and 7. All right. And then for this particular graph, let's find out the degree of each vertices. Yeah, of each vertex. A, B, C, D. The degree of A, B, C, D. 3, 3, 3, 3, 5. And we total up all this, we definitely become an even number. In this case, when we total up, we get 14. So this theorem is correct. This is what we observe. Yeah. So this is a separate theorem. This is a separate theorem. Just now the theorem is that in order for the Euler graph to be, in order for a graph to be a Euler graph, in order for any graph to be a Euler graph, every degree must be odd. Every degree must be odd. Sorry, every degree must be even. Every degree must be even. Yeah, not odd, even. If it is not even, then sorry, it is not a Euler graph. Okay, the second theorem is that it's totally different, not related to the first theorem. Every time we add up all the degrees, you get an even number. Even though the individual degrees may be odd, yeah, you get even number, no matter what. So Euler cycle is one of the types of graph. Yeah, the other type is Hamiltonian. If you can remember Euler well, you'll be able to remember Hamiltonian as well. Yeah, so Hamiltonian is based on a problem called traveling salesperson. Now, as a salesperson, you meet customers because the more people you meet, the more customers you can find, right? And to meet these customers, you need to travel. And to save your costs, you want to find the simplest route. Yeah, you want to reduce the number of routes you take to visit all the customer one time. You just want to meet them one time only. So what is the minimum number of routes to meet every customer one time only? So this is a graph problem, right? You see, let's take this as an example. Let's say we have our customers. We have 6 customers: customer A, B, C, D, E, F, G, which live in different locations. So as a salesperson, he or she needs to travel to meet every one of them. He may be driving to A, and then from A he drives to B, B drives to C, C drives to D, D drives to E, E drives to F, F drives to G. Seems like a waste of traveling trip, right? Because he could have go to A, B, G, D, C, E, F, which can reduce the distance of travel, right? So this is what Hamiltonian cycle is about. We want to visit every vertices exactly, not at least, exactly one time. But we don't care about the edges. If there's a need to use the same road twice, no problem. Because Hamiltonian is just about the vertices, not about the edges. Euler is about the edges. Euler is about the bridge. It's about the edges. But traveling salesperson is not about the road you take. It's more about meeting the customer, the vertices. All right. So now you have just been introduced to Hamiltonian, and let's take a closer look at the differences between Hamiltonian and Euler circuit again. Remember this, for Eulerian circuit, yeah, you must travel every edge exactly one time. Every edge exactly one time. Whereas Hamiltonian is not about that. Hamiltonian is the opposite. It's not about the edge, it's about the vertex. Every vertex exactly one time. That means you don't care about the edge. You want to skip it, you want to cross it 2 times, 3 times, 1 time, we don't care. Yeah. How about Eulerian? Eulerian is about crossing every edge exactly one time only. So we want to go back to the same vertices more than one time, doesn't matter. We are just concerned about edges only. Eulerian, every edge exactly once. Yeah. So there you go. I hope by now you're able to grasp the difference between Eulerian and Hamiltonian graphs. For Königsberg, Eulerian is definitely the choice because we are concerned about the edges. Yeah, you're concerned about the connectors. Whereas for Hamiltonian, we are concerned about the target nodes. Yeah, not the route, but the target, the vertices. So let's look at one exercise. Let's study this graph. This graph has how many vertices. We have A, B, C, D, E. So apparently we have 5 vertices. How many edges we have here? Wow, quite a number of edges. We need to count. Yeah. The edges, if we count systematically, A, there's a loop there. That's also considered an edge. 1, 2, 3, 4, 5. Okay. Do I miss out any? 5. Let's count again. 1, 2, 3, 4, 5. So there are 5 edges for A. Okay. And then for, let's go to B. We don't count the similar ones again. 5, 6, 7, 8. Go to C. 9, 10, 11, 12. And finally from D to E, 13. So they are, if you count nicely, yeah, if it's on a piece of paper, you just tick those edges that you have counted. There should be about 13 edges. How about the degree of each vertex? This one you have to, again, you go one by one, A, B, C, D, and you count the number of incident. Incident means edges that are connected to it. Like for example, if this line, if you look at my mouse cursor, this line between D and C is so remote from A, right? So definitely it's not an incident edge for A. It's not an incident edge for B, but it's an incident edge for D and C, right? So let's look at the answer. Okay, degree for A is 6, right? 1, 2, 3, 4, 5. Yeah. You see here? Because it is a loop, right? A loop is actually one going and one coming in. One going and one coming in, right? So therefore we consider it as 2. Yeah. So therefore the total is 6. 1, 2, 3, 4, 5, 6. Yeah. How does this happen? Remember, a loop is going and coming in, right? One going out, one coming in. That's why it's considered as having 2 degrees. You see? 1, 2, 3, 4, 5, 6. I repeat. 1. Look at the cursor. 1, 2, 3, 4, 5, 6. How about B? Okay. 1, 2, 3, 4, 5, 6. Yeah. And then how about C? 1, 2, 3, 4. Is it 5 going out, 6 coming in? So C, degree of C is also 6. How about D? D is simple. 1, 2, 3, 4, 5. How about E? 1, 2, 3. So there you go. That's how you get the answer. Now this is a undirected graph because there are no arrows. Now in this example, we are dealing with a graph with direction. Graph with direction. How do I know it has direction? Well, very simple. You see there are arrows. Previously, all the other graphs has no arrows. They are not digraph. They are not directional graph. Now we are looking at a directional graph. So when we have a directional graph, right? Then we will be there'll be 2 types of degree. One is in degree. The other one is out degree. Just now, we were just counting the degree, right? We don't care whether it's going in or going out because there's no information. It's just the same. There's no information whether it's going in or going out. So in the second example, we have 2 types of incident edge. One is going out. Like for example, for the vertex A, right? As you can see here, this edge is going out. So this is out. The second one is also out. Third one is also out. But the fourth one is in, right? Yeah. The fourth one is in. And how about this one? This one is also in, right? Yeah, this one is also in. So the in degree will be 1, 2. How about the out degree? You see, loop has two degrees, right? One is out, one is in. So out degree 1, out degree 2, out degree 3, out degree 4. Now how about B? Okay, B. Look at B. How many in degree coming inside? 1, 2. How about this one? This one doesn't count. This one is going out. So that the in degree is 2. The out degree, apparently only 1. No more already after that. So what out degree for B is 1, in degree for B is 2. Now, please try to figure out for C, D, E, and F. Do you know what is the answer of F? Anybody? Any incident edges in and out? None, right? So basically it's 0. Yeah, the degree of F is 0. The in degree 0, out degree of course 0. We are in the final subchapter of graph. Yeah, the final subchapter of graph is about representing graph as matrices. Yeah, as matrices. There are 2 types of matrices that you are required to know. Number 1 is adjacency matrix. Then the second one is incidence matrix. Now, what is adjacent? Adjacent means neighboring, adjacent. Yeah. For example, when you are seated in the lecture hall, you may have a neighbor, right? So that neighbor is adjacent to you. Yeah, sitting adjacent to you. So imagine you are a vertex. Your neighbor is a vertex. Yeah. So both of you are vertices. I mean, you may have more than one neighbor, right? Maybe the neighbor on your left, the neighbor on your right, neighbor behind you, the neighbor in front of you, or you may be just having one neighbor to your left, but none to your front or back. Yeah. So let's analyze the neighbors of each of the vertices. Let's look at this example. Yeah. So we have vertices V, W, X, Y. Yeah, V, W, X, Y, and then with edges E, edges F, edges G, H, J, and H, H. All right. Now, in adjacency matrix, we are concerned only the vertices which are next to one another. Like in the analogy just now, I said that in this lecture hall, you are seated there, and then you may be having neighbors just next to you, right? So these neighbors are your adjacent vertices. Yeah, these neighbors are your adjacent vertices. So in adjacency matrix, we want to study the adjacency between the vertices. So what do? You have in the rows V, W, X, Y. We only look at the vertices. We are not bothered by the edges because we're just studying the vertices. Yeah. And then on the columns V, W, X, Y, we're repeating them. Now, this is what we do. Is there any connection between V and V? Is there any loop? No. So that means 0. Is there any connection between V and W? Yes. Is there any connection between V and X? Unfortunately, no. You see there's no line. So X is not next to V, right? Is there any connection between V and Y? Yes. So you put 1. Now, then you go to the second row, W, you repeat again. Is there any connection with V? Yes. Any connection with itself? There's no loop, right? No. Any connection with the X? Yes. Any connection with Y? Yes. So you repeat this for X and Y. Okay, let's look at the last one, Y. Any connection with V? Yes. Any connection with W? You see, just systematically follow. Yes. Any connection with X? Yes. Any connection with itself? No. So the matrix is produced simply by studying the connection between the vertices. If there's none, you put 0. If there is, you put 1. And there you go. You have just produced a matrix. This is what we call a matrix. Yeah, a matrix is basically this is a 2D matrix, right? A 2D table. The other type is called incidence matrix. It looks very much like adjacency matrix, which is why you have to be careful about the difference. Now, as you can see here, we are still using the same graph for both. Yeah, but we want to produce a different kind of matrix called incidence matrix, not adjacency. Incident matrix, we are just studying about the edges. We're not talking about the neighbors. We're not talking about the vertices. We are just talking about the incident edges. Remember incident edges is now the word incident where it was used in the earlier of the lecture. Yeah. So along the column, along the rows, okay, same. Just like adjacency matrix, we have the vertices, but along the columns, look here. We are not putting vertices along the columns. Yeah, these are edges. Edges E, F, G, H, and J. You see that? Now, this is how we do it. Let's go one by one. V. Is there any H, E? Yes. Is there any H, F? Yes. Is there any HG connected to V? None. So 0. Any HH connected to V? No. Any HJ connected to V? No. So you see, we already produced the elements, the values for V, vertices V. Now we move on to W. Yeah, W. Any incident edges E with W? Yes. Any incident edges F, E, G, J? No. Any incidents G with W? Yes. You see, E, G, G. Any incidents of H? No. E, J, J? No. So any incidents with J? Okay, apparently. So we will repeat the same. Yeah, we repeat the same for the rest of the vertices X and Y. Why we want to convert graph to matrix? Well, earlier we want to convert from problem to graph, right? And then from graph to matrix. The reason is that in software, in programming, it is the format that can best represent a graph. Yeah, matrix is suitable because we can use 2D array of any variable, whether it's integers or string, and you can produce matrix easily just by using 2D array. So let's try to look at another example, another exercise. How many vertices we have here? We have 4 vertices, A, B, C, D. Let's use adjacency matrix to represent the above graph. Do you still remember adjacency matrix? Adjacent means neighboring vertices, yeah? A, B, A, C, A, D. So we need to draw a matrix of vertices versus vertices. Now, incidence matrix. Incidence is about incident edges, right? So we need to draw a matrix of vertices versus edges, not versus vertices, not vertices, but vertices, edges. All right, and then you analyze whether the edge is connecting to the vertex or not. So please try to do this, and then you may want to pause this video. And once you are done, you may proceed to see whether your answer matches the matrices in the answer. All right. Okay, I hope you have done. And let's look at the answer. Let's look at the solution. I hope you get the same answer as this. Yeah. All right. So as you can see here, this is a 2D array, right? Matrix is a 2D array. Yeah. So you can have a binary 2D array in a programming environment, and you can do programming. You can apply code to the graphs. Yeah, doing matrix operations on them easily because you can represent them. Yeah, in the form of matrix. And the two types, one is adjacent, the other one is incidence. Adjacent is vertices. Incidence is vertices, edges. All right. So finally, we have reached the summary slide. Yeah. Let's go through the points and see whether we have covered, and if you have understood. If you're not able to recall, probably you want to go back to the earlier parts of this video in order for you to recall, and hopefully my explanation will help you to understand it better. Number one, a graph G has two components, yeah, vertices and edges. A graph is a non-linear data structure that consists of nodes and edges, and nodes B, edges E. And the nodes can be objects, yeah, and then the edges are links. Number two, a graph can be simple, weighted, or directed. There are a few types of graph, yeah. And then number three, a graph is a data structure for modeling problems and has been used in various applications. Okay, Königsberg bridges is one of the application. How flags can be connected, another example. Yeah, there are many more. Number four, degree of a vertex refers to the number of incident edges. Okay, so we can actually give numbers to every vertex by counting the number of incident edges. Yeah, if we're talking about bidirectional graph, then we are just talking about degrees of each vertices. But if we're talking about directional graphs where there are arrows of in and out, then we may want to count incoming degree or outgoing degree. Yeah, these are two different. One is outgoing arrow, the other one is incoming arrow. And remember, a loop, a loop edge is made up of one incoming, one outgoing, and it's always considered as 2 degrees. Yeah, one incoming degree, one outgoing degree. Two types of cycles are Euler cycle and Hamilton cycle. Which one do we use for Königsberg bridges? Euler cycle. Euler cycle is about the edges. We cannot, the edges, every edge exactly only once. Whereas Hamilton is not looking at the edge. Hamilton is looking at the vertex. The vertex must be visited exactly once. Okay. And then finally, a graph can be represented using matrix. Why? Because in programming environment, in computing environment, we can use 2D array or 3D or even more to create a matrix conveniently. So we want to represent graph as matrix so that we can transfer the representation into coding representation. And there are two types of matrices that have been introduced to you in this lecture. Number one is adjacency matrix, whereby we are comparing vertices against vertices, and then the other one is comparing vertices against incident edges. So that's about it for our lecture. Any questions, students? You may post them in the comment below, and I will answer them. I hope you have gained something from me. Yeah, at least these are the things that you should be bringing home. Thank you very much. Thank you for having me here. Have a nice day. Thank you.